try it in the lab and we'll see what happens. Alright, so here's calcium carbonate. Looks like a white powder. Looks very similar to the ammonium carbonate before, right? So you look back, we had ammonium carbonate, calcium carbonate, both carbonates, similar kind of substances. They look pretty similar. Alright, so let's see if we get anything produced here when we react it with hydrochloric acid, because that's what we're going to do, reacting with hydrochloric acid. And again, if you need to stop and pause the video so you can write these down in your worksheet, then make sure you do that. Okay? So calcium carbonate. Here's my hydrochloric acid. So you can see we've got some more bubbles, so another gas being produced. Bit more acid there, so you can see that reacting very well. So let's do our flame test again to see if we get something similar happening. Because remember, the flame test before made a nice pop, right? So let's try this one. Did not make a pop. Matter of fact, it put the gas out, or put the flame out, right? So the gas was kind of extinguishing the flame. So in our reaction page that listed those gases, the test that indicates that flames are put out by a gas is indicative of carbon dioxide. If you know a little something about fire extinguishers, you know there are some fire extinguishers that are called CO2 extinguishers. That's because they have carbon dioxide in them. Carbon dioxide pushes the oxygen out, and if you don't have oxygen, things can't burn, right? Oxygen is part of one of the components of the fire triangle. On a fire triangle, you need something to burn, like paper, wood, gasoline, something like that. You need oxygen, and you need a source of energy, a flame, a spark to get it going, right? If you take out one of those three, like you remove the oxygen, you don't get anything to burn. Okay, so carbon dioxide removes the oxygen, so it stops the flame from burning. So let's go over and check our chart then. So I know I would have CO2 gas being produced. Okay. Something else that may be a little tough to see here, but I think you can also see there's droplets up here. Okay, that got produced. Can you see those? That indicates we've got some water in the reaction as well. And then if you take a look at my reaction, I've got two other elements here that aren't indicated by the products yet. So we have to account for those because of conservation of mass, right? So we know that everything has to be accounted for. So this calcium, which is on the left side of the formula, must be a positive ion. Chloride, which is on the right side, is a negative ion. So that is my other product here, calcium chloride. And again, if I'd go back to a periodic table, I'd see calcium is in column 2, like the magnesium was up here, has a +2 charge. Chlorine, we had already said, had a -1 charge. So since calcium and magnesium are in the same columns, we're going to have a very similar formula here. I'm going to need CaCl2 to balance that charge. All right? Carbon dioxide and water all come from the CO3 and the H ions here. So how do we balance it then? I have 2 Cl's, so how do I get that to balance here? I have to put a 2 in front of the HCl, right? And that gives me 2 H's, which was what I needed to make the water, right? I've got a C here. I got 3 O's. I only have 2 O's here, but I have 1 in the oxygen. So there's 3 oxygens and 3 oxygens, 2 hydrogens, 2 hydrogens, 2 Cl's, 2 Cl's, 1 Ca, 1 Ca, 1 C, 1 C, and I have it balanced. Well, what kind of a reaction is that, though? All right, what kind of a reaction? Well, if you notice, it looked like the Ca and the Cl kind of bonded together, right? And that could happen if the Ca and the H switch positions. So that's that exchange, right? But then what happened with the H and the Cl3? Well, there's a couple things that happen in there, and this is an example where maybe this reaction doesn't fit our pattern of one of the 5 perfectly. But what did exactly happen here is that this H ion and the CO3 came together. So they really form H2CO3. The 2 H's and the Cl3 form hydrogen carbonate. The thing is, though, the hydrogen carbonate doesn't exist very long. It quickly breaks up into carbon dioxide and water. And you should be able to see how these come from this. I've got the CO2 coming from CO3, and the 2 H's and the extra O form the water. It's actually something very similar that happened up here. Okay? My CO3 produced CO2. I have a CO3 produce a CO2. All right? And the hydrogen came off to help me form some water here. And this reaction actually ends up giving me NH3 plus water out of NH4OH. So you can see it's a very similar kind of reaction when you get right down to it. This one's probably a little more like a double exchange, okay? Whereas this one really didn't exchange ions, it just kind of broke apart and formed some new compounds. And so this one, number 3, is an example of a decomposition. We forgot to label that a couple minutes ago when we did that. So I have an example of a combination, a single exchange, a decomposition, and now a double exchange. So we've got an example of all 4 of the 5 major types. We haven't done the combustion one yet. That's coming down here as we continue on. All right, let's keep going. Again, we're getting kind of long here, so I don't want to take too terribly long. Copper chloride and zinc. Let's do that reaction. So copper chloride is a blue solution, okay? And so I will take some of that and put it into a test tube. And zinc. Hold my forceps here. So it's kind of a gray silver piece of metal. It's a pretty hard chunk. Okay. So I'm going to put that into our test tube with copper chloride. And we look and see, doesn't appear to be much happening here. Looks kind of boring. I don't really see any bubbles. No energy change. Well, this is a reaction that is a lot slower than some of the other ones that we had. The first 4 that we had, they happen almost instantaneously. So this one, let's put it down for a couple minutes. We'll come back to it towards the end and see if we get a change that's a little more noticeable, because it is one that takes a little bit of time. All right? So I'll set that one off to the side, and we'll come back and look at that in a few minutes. So let's keep going. I'll come back to my charts here. So this one we're going to let set for a few minutes. Number 6, copper chloride. Again, we use that same blue solution, and sodium phosphate. So let's try those 2. And if you look at those reactants, you might already be able to predict what kind of a reaction is going to be. So here's my copper chloride solution. Get a little of that in the bottom of my test tube. It was hiding behind the zinc bottle. Here's my sodium phosphate. If you look, it just looks like a clear liquid. Looks almost like water. Okay, it is a solution. Sodium phosphate dissolved in water, but doesn't have any coloration to it. So let's take a look at my blue copper sulfate, adding sodium phosphate to it. And you'll notice that it turned cloudy. Okay. Now things that turn cloudy are generally turning cloudy because they have a fine precipitate, a solid that's kind of floating around in the liquid. Remember, precipitate was a term that we used to describe a solid that produced. So we're going to indicate that I've got a solid being produced here, a fine powdery thing that's kind of floating in the liquid. If I let that settle for a few minutes, we might be able to see that solid being pulled down by gravity, make it a little more obvious. Okay? But at least I've got a color change. All right, I've seen that. It's kind of a whitish color now. And I've got evidence of a cloudy solution, which means I have a new solid producing, a precipitate. So I've got those two evidences of a chemical reaction. Okay? So let's come back to my previous one. Okay? My copper chloride and zinc. Can you see any change to it? If you notice, the zinc looks very dark in color now. It's not that silvery gray material. Again, I don't know how well it picks up on the video, but it's kind of like a reddish brown material. It's a very dark reddish brown, almost like a brick color kind of material that's forming on the outside of the zinc. And I don't know if that looks familiar to any of you, but if you look at my reaction, okay, this looks like it's going to be a compound with an element. So that's very similar to compound with an element, a single exchange. So if I get a exchange here, the zinc and the copper switching places, I should have copper metal being produced. If you remember from other reactions, or think of the color of a copper penny, it's kind of that dark reddish brown brick kind of a color. And so yes, I do have some copper being formed on the outside of my zinc. Okay? So if I were to do my reaction here, I'm going to get the copper and the zinc switching places, right? My single exchange. So I would have zinc now bonding with the chlorine and copper by itself. And again, do I need subscripts? So I have to go back and check charges. If I go back and look at my yellow sheet, I'd find that zinc has a +2 charge. Chloride again, only a -1. So I do need a subscript there. So I have calcium chloride, zinc chloride, magnesium chloride. They're all very similar compounds because zinc, Ca, Mg, all have a +2 charge. So I'm going to need a subscript 2 behind each of those. And then I need to balance. Okay, I've got a copper and a copper. That looks all right. Copper chloride already had 2 Cls. Zinc chloride has the 2 Cls. So let's balance, and a zinc and a zinc. So that one I didn't need to balance anymore. Okay, a single exchange or a single replacement reaction. Okay. In my 6th reaction, copper chloride and sodium phosphate, what kind of a reaction do you think that one is? Is it like this, where I have an element and a compound? Where I have an element switching places? No, so I don't have an individual element here. All right. Is it like a decomposition? No, because I've got 2 compounds here. This only has 1 compound. If I only have 1 compound, all I can do is split apart into things. Okay? And it's not 2 individual elements getting put together. I've got 2 compounds already, and they're never going to be put all together. You would never find all of these things all in one compound. Very, very unlikely. So it looks like it's going to be that double exchange, very similar to number 4, where I had a compound, and the 2 sets of ions switch places. So let's see how that would work in this reaction.